somewhere, there may be another version of you. A version that made the decision you were too afraid to make. A version that said yes. A version that said no. A version that became rich. A version that failed completely. A version that never met the people you love. And maybe a version watching this same video right now. It sounds like science fiction, but one serious interpretation of quantum mechanics suggests something disturbing. Maybe reality does not choose one outcome. Maybe every possible quantum outcome actually happens, and if that is true, then the question is no longer, what will happen? The question becomes, which version of you will experience it? So today we ask, are there infinite versions of you? For centuries, scientists believed the universe worked like a machine. If you knew where something was, and how fast it was moving, you could predict what would happen next. This was the world of Isaac Newton, a falling apple, a moving planet, a cannonball, a pendulum. Everything had a position. Everything had a direction. In that kind of universe, the future was hidden, but not mysterious. It was like a book already written. You only needed the right mathematics to read the next page. But then scientists looked deeper. Not at planets, not at apples, not at cannonballs, but at atoms, electrons, particles, the tiny building blocks of reality. And suddenly, the machine broke, because at the smallest level, things did not behave like solid objects. They behaved like waves, not exactly here, not exactly there, but spread out, possible here, possible there, possible almost everywhere. And that created one of the biggest questions in science. If a particle exists like a wave of possibilities, why do we only ever see one result? In quantum mechanics, a particle is described by something called a wave function. Think of it as a mathematical cloud of possibilities. It does not tell you exactly where the particle is, it tells you where the particle could be found. And the strange thing is, this wave function follows very precise rules. It evolves smoothly, it spreads, it moves, it changes according to the Schrödinger equation. But here is the problem. We never actually see the wave function directly. We do not observe a particle spread across the room. We observe one click, one mark, one result, one location. A physicist named Max Born gave the wave function its most famous interpretation. He said the wave function does not show where the particle definitely is. It shows probability. At every point, the wave function has an amplitude, and if you square that amplitude, you get the probability of finding the particle there. This became known as the Born rule. And it worked, spectacularly. But there was a cost. The universe no longer seemed fully deterministic. Reality now seemed to involve chance, probability, uncertainty. The traditional way quantum mechanics is often taught has two very different rules. Rule 1, when nobody is looking, the wave function evolves smoothly. Rule 2, when someone measures it, the wave function suddenly collapses. But why should the universe have one rule when we are not looking, and another rule when we are? What makes a measurement special? A machine, a scientist, a human mind, a camera, an eye? This is called the measurement problem, and it leads us to one of the most famous cats in history. In 1935, Erwin Schrödinger created a thought experiment. A cat is placed inside a sealed box. Inside the box is a radioactive atom, a detector, a vial of poison, and a mechanism. If the atom decays, the detector notices it, the poison is released, and the cat dies. If it does not decay, the cat lives. But quantum mechanics says the atom does not have to be only decayed or only not decayed. Before measurement, it can exist in a superposition of both, decayed and not decayed, at the same time. Today, people often use Schrödinger's cat to show how weird quantum mechanics is. But that was not Schrödinger's original point. He was not celebrating the weirdness, he was attacking it. To understand why scientists take superposition seriously, we need the double-slit experiment. Fire electrons one by one toward a wall with two slits. If electrons were ordinary particles, we would expect two bands. But that is not what happens. Instead, over time, the electrons form an interference pattern, a pattern you would expect from waves. It is as if each electron somehow passes through both slits at once, interferes with itself, and only appears as a particle when it hits the screen. That sounds impossible, but experiments force us to take it seriously. So superposition is not just a fantasy, it is one of the most tested ideas in modern physics. Now we meet another strange idea. Entanglement. Entanglement happens when quantum systems interact in such a way that they can no longer be described separately. Measure one, and you instantly know something about the other. This matters for Schrödinger's cat. The atom becomes entangled with the detector. The detector becomes entangled with the cat. The cat becomes entangled with the box. And eventually, when you open the box, you become entangled too. So maybe measurement is not a magical collapse. Maybe measurement is just entanglement spreading. Maybe when you look inside the box, you do not force reality to choose. Maybe you become part of the result. In 1957, physicist Hugh Everett proposed a radical idea. What if the wave function never collapses? What if every possible outcome actually happens? When the atom decays, one branch of reality contains the dead cat. When the atom does not decay, another branch contains the living cat. And when you open the box, there is one version of you that sees one outcome, and another version of you that sees the other. Both are real, both continue, but they can no longer interact. They are separated into different branches of the universal wave function. This sounds insane, but supporters argue that it is actually simpler than collapse. No sudden collapse, no special observer, no magical measurement, only the wave function evolving according to the same rule. But many worlds does not mean everything imaginable happens. An electron does not randomly become a lion. Physics still has rules. Some outcomes are possible. Some have almost zero probability. Some are forbidden. So many worlds does not mean fantasy becomes real. It means every quantum possibility allowed by physics may exist in a different branch. Reality is not a single road. It is a tree, branching, splitting, growing. So, are there infinite versions of you? The honest answer is, we do not know. Many worlds is an interpretation of quantum mechanics. It uses the same mathematics that already works, but whether those branches are real in the way our world feels real is still debated. But if many worlds is true, then the version of you listening to this sentence is only one branch. There may be another you who clicked away, another you who never found this video, another you who became exactly who you dream of becoming. But you will never meet them, because from your perspective, you only experience one path, one branch, one stream of consciousness, one version of the universe. Schrödinger's cat was meant to expose a problem. A cat cannot be both alive and dead, at least not in the world we experience. But maybe the deeper lesson is not about cats. Maybe it is about reality itself. Maybe the universe is not choosing one story. Maybe it is telling every story. And we are only reading one page. Science has not proven infinite versions of you exist, but quantum mechanics has made the question serious enough to ask, because maybe somewhere, in some branch of reality, another version of you is asking the same question: am I the original, or just one of many? So, are there infinite versions of you? Maybe, maybe not. But if reality really branches every time possibility becomes experience, you are not just living a life. You are living one version of a story that may never stop splitting.